Every day at school, Joe climbs a flight of 6 stairs. Joe can take the stairs 1, 2, or 3 at a time. For example, Joe could climb 3, then 1, then 2. In how many ways can Joe climb these stairs? I'll give you guys about a minute to think about this. Try to pause the video now. All right. So basically what this question is asking, how many ways are there to express 6 as 1s, 2s, and 3s? So here would be one possible way. There. Okay. What about another possible way? Let's do 1 plus 2 plus 3. Note that order does in fact matter. So that would be different. Okay, so we're going to take 2 approaches. If you already know how to solve this using casework, go ahead and skip to the recursion part. And if you already know how to solve this using recursion but don't know in casework, keep watching. Note that the casework solution is much faster than the recursion solution, but both are good to know in the future. So here's the casework solution. So there's like some possible values. The first case is where there's 6 1s, 0 2s, 0 3s. Let's actually just make a table for this to organize our work. This is like the number of 1s, 2s, and 3s. So we could have 6 1 0 0. You could have 3 0 1. You could have 0 3 0. You could have 0 0 2. This is a lot of cases, so let's try to restart this, but this time let's organize it based on the number of 1s. Starting with where there's 6 1s, and then we can go to 5, then 4, then 3. Okay. So the first case is when there's 6 1 0 0. Next case, and so I'll just put an example on the side. Oops. 6 1s like that. Okay. The next case is if there's 5 1s. But then we know that there has to be 6 1s. So there can't be a 5. So I'll just X that out. Okay. Now 4. Then it's exactly 4. So then we have 2 remaining. And so there's only one way to do that with this 2. So let's just do that. So here's a possible value. Note that order still, as I said previously, order still does matter. So there's going to be 1 possible value for this, 5 possible values for that. Okay, next case is there's 3 1s, which means that there's 3 left. And there's actually only one way to do this without doing 1s. You can just do a 1 3 like that. Here's the possible value. Oops. And there's 4 ways to do that. So far we've obtained 10 ways. Okay, now let's do 2 1s. This is getting slightly harder because we need to get 4 with only 2s and 3s. So let's just look at the possible values. 2 plus 2. Okay, so that's actually not too bad. It's just 2 plus 2 because if we know that if we use a 3, then we must have to use a 1 and we can't use any more 1. So just 2 plus 2. So in this case, we'd have 2 2 0. And here's a possible value. 1 1 2 2. We know that there's 6 values for that because 4 choose 2. Okay, so now our running count is at 16. And actually, there's 2 more cases remaining. So now we have to make 5 with 2s and 3s. If we want to use a 3, just 3 plus 2. Is that the only way? Let's see. So if we use a 3, then we must use a 2, and we can't do it with just 2s. So yes, that's the only way. So 1, 1. So then that possible value for that is 1, 2, 3, of course. And there's 6 ways for that. Okay, so far, I'll just keep, so far we have 22, and we have one more case. 1 zeros. So then how do we make 6 using 2s and 3s? So there's a 2 plus 2 plus 2. That's the case with only using 2s. Or you could also have a 3 plus 3. So there's 2 ways. So then we can see that we can sum those and we'll get 24. So that's one way to solve it, except in my opinion, this is slightly inefficient because what if we had like 10, say? If we had 10 possible, and if Joe was climbing 10 stairs instead of just 6, this would actually be much, much, much harder. Okay, so before I was talking about a recursion way that's more efficient. So what even is this recursion way? So to start, we define A of n. Okay, so let's just define A of n to be A of n is the number of ways Joe can climb n stairs. So let's do some casework. This recursion and casework, they're all combinatorics, but recursion, there's not nearly as many cases. So let's just say the first time Joe climbs it, let's say his first step is a 1. So like 1 plus ... 6 is equal. So then this is basically just A of 5, right? So A of n is equal to A of n minus 1 plus, but what if you do a 2 first? That's just A of 4, right? A of n minus 2. And same for A of n minus 3. It'd be same for if you do a 3 first. That'd be A of 3. Ways to cover those 3 stairs remaining. So now we have this recursion. What can we do? Well, we can start by seeing that A of 1 must be 1, right? Of course, there's only one way. 1 is equal to 1. What about A of 2? So 2, you can do 1 plus 1, or you could just do 2. There's 2 ways. A of 3, it's going to be 4. 3 is equal to 3. 3 is equal to 2 plus 1. 3 is equal to 1 plus 2. Or 3 is equal to 1 plus 1 plus 1. Okay. So now that we have that, let's go see A of 3 is equal to 4. So then A of 4 must be equal to 7 because of this recursion. A of 5 is equal to 13. A of 6 is equal to 24. That's our answer. And notice that this is much more efficient than the casework method, because what if they asked us for, say, A of 7? We could instantly calculate it by summing 7 plus 13 plus 24. It's going to be 44, by the way. But using casework, we'd have more cases that may add up and become really hard to manage. Okay, so that's it for this video. The next time you're tackling a combinatorics math problem, make sure to think recursion before you just go ahead and grind with casework, because right now we experienced how recursion was much, much, much easier than casework. Make sure to subscribe if you like this video. Thank you. Bye.